It's called A Journey into Flash Memory, and how actually an industry contract turned into new C64 game cartridges. My name is Jens Schönfeld. I run individual computers for quite a few years now, almost 25 years. I grew up with the C64, the Sirius Victor 9000, a machine designed by Chuck Peddle, who also designed the 6502 processor, and of course the Amiga. I studied electrical engineering at the University of Aachen, which later, after I left, turned into an elite university. I don't call myself a programmer, but I write code every now and then, but I know my limits, and that's why I'm here. I want to discuss with you, programmers, what's allowed and what's possible on the C64. Those of you who did follow me in the past few years might know that I have refused pretty much every contract work in the past few years because I just wanted to focus on my retro stuff. This has changed now, but conditions apply. We'll get to that later. In 2022, I got a consulting request to procure components for a 68HC11-based system. This system is, of course, the 68HC11 is an 8-bit computer. Usually it has 64K address space, so they added some banking. They had a total of 1 megabyte of flash memory in that system. The system uses an external bus frequency of 2 megahertz, and essentially their request was, can you supply 80,029 F040B chips? It turned out that one of their employees has bought a GMod 2 cartridge with the game on, opened it up, and found that Individual Computers has made this. We're using the exact same flash chips that have been made for that have been requested for this contract, and therefore this company contacted me. Now, first thing I did was I checked what's available, and because I just wanted to know what's available on the free market. I only found a single vendor that is still making 5-volt flashes, and that is Alliance. DigiKey actually only has 1,500 in stock right now, so far from the requested 80,000. And if you look at the price, that's still over $5 if you are buying more than 1,000 units. So more than $10 for 1 megabyte of flash, that's a showstopper. So why does it have to be parallel flash anyway? Back in the days of the 68HC11, it was really the way to go. It's really easy to use for the designer because you just connect the address bus of the CPU to the address bus of the flash. You connect the data lines for the return also directly to the bus. It's all 5-volt devices, and therefore there's nothing that you need to implement, nothing that you need in the middle, no level shifters or what. And the requirement of the 68HC11 is fairly relaxed. Although it's a 2 megahertz bus, you don't have the full time of the 2 megahertz because it's multiplexed. It comes down to about 270 nanoseconds access time, which is plenty for the speeds that Alliance is offering. This is, I believe it was 55 nanoseconds for the fastest ones. But of course there are drawbacks. It's only from one manufacturer. It is insanely expensive, $10 for 1 megabyte. That's just not what you can do. And of course, it wasn't available in the requested quantity. So I investigated 3.3 volt parallel flashes because that's the easier part. You could just use level shifters in between, and yeah, but I couldn't find any viable advantage, anything that would work without code changes, and therefore I quickly decided that's a dead end.
Why are code changes necessary here?
Because they are also writing settings into the flash. And writing into the flash is always different depending on vendor. If you only use the same type from a different vendor, then you might only need to change an ID. But if you go a completely different chip, like in this case, a 3.3 volt chip, even 16-bit wide variants that I investigated that can be switched to 8-bit, or with a little bit of logic, you can turn them into an 8-bit thing. That would require bigger changes, and the person who wrote the code was not working for the company anymore. So, I mean, they had isolated the part that writes, and were actually willing to do this. But again, price-wise, it wouldn't be an advantage, and therefore, I decided that that's a dead end. Now, the next one would be investigating current flash technologies, because USB sticks are really cheap. I mean, €10 budget, that buys you several 10 gigabytes these days. But, and of course, that NAND flash, that's available everywhere. It's even standardized. ONFI, that's a consortium that standardizes the command set of how to talk to these chips. But you cannot just apply an address and get your answer within a few nanoseconds. But you have to read a whole block, you have to do error correction, and that just doesn't work for direct code execution from flash. So NAND flash, still a dead end. Don't worry, it's going to get sillier with the with the memes. Now, the current flash technologies, they also have okay. Of course, you are used to our hardware getting cheaper and cheaper by the year. And that's, of course, a result of silicon structures getting smaller and smaller. You might have heard that, that they're already producing, I mean, standard NAND flash, they are producing in 18 or even 15 nanometers, but the 29 F040 chips that were originally requested, they are made in a 350 nanometer process. Now, if you shrink the size on the chip, on the die area, on the silicon area, that means your number of bits that you can fit in there grow with a power of 2. So if you halve your structure size, you increase your available memory by 4. And that, of course, requires more and more pins. And pins can only be arranged at the circumference of the chip. That's where the bonding happens, the bonding, the connection of the actual silicon to the package. And those bonding pads, they cannot be shrunk. They still have the same sizes. They are about 60 by 60 microns, and of course, you need a certain distance between these. Some chips use staggered arrangements, but in essence, it's like you have those tiny chips, and you need a huge number of pins around it for a parallel flash. And if you just want to have 1 megabyte, then you end up with a lot of unused chip space, and all the advantages of the better process that is available are just not available. So what's been established in the industry now is SPI flashes. You see that little picture, that 8-pin thing? These SPI flashes are really cheap, they're abundant, they are NOR flash. That means the capacity is slightly smaller, but they guarantee error-free reads. You do not need any error detection or error correction. They are more expensive, but you can buy 1 megabyte chips for under 10 cents. That's really 10 cents versus $10 that we explored before. They're available from a lot of manufacturers. And the command set is standardized. And the good thing is they are really available. Even through the chip crisis, these chips have been available. But it is serial, and that's slow. But is it really slow? He has doubts. So let's look at how an SPI flash wants to be talked to. Let's assume 50 megahertz clock, because that's about the fastest you can go with this standard read command. You need 8 bits in order to clock in the command, then another 24 bits to clock in the address, and another 8 bits to get your actual data. And that ends up at 40 clocks. 800 nanoseconds at 50 megahertz. And that means failed. So there is a fast read command. This fast read command allows higher frequencies, but it requires you to insert a few dummy cycles. So you clock in the command, clock in the address, then a little pause, 1 byte pause, and then you can pick up the data. That means you need more cycles, but you can run at a higher frequency. So we can crank up the speed to 100 megahertz, and we end up at 480 nanoseconds. Getting better. But that's, of course, still not 270 nanoseconds, which is required. Now, these chips can reuse their pins. They can turn around on the command pin. That's what I'm showing here. The data in signal can turn around and be used as a data signal as well. That means I still have the same start, I still have the same dummy cycle, but my data is coming in at 4 cycles only. That's shaving off another 40 nanoseconds. Still not there, but these chips can do more. With a different command, I can clock in the address also on 2 pins of the chip. And that shaves off another, well, over 160 nanoseconds of the time at 100 megahertz. But I actually want to run at 50 megahertz because that makes things a lot easier. Why? We'll get to that later. So yeah, 280 nanoseconds is coming close to where we need it to be. But these chips can do more. You've seen that they have 8 pins, 2 of them are for power. So the other 2, I've already written them, I've already mentioned them in the timing diagram below. That would be the quad commands, meaning those previously unused pins can also become data pins. So they kind of become parallel now, because I can use 4 pins to clock in the address. Of course, I need dummy cycles, because the chip needs to find the data before it can output the data. But still, you gain something. At 100 megahertz, you're even faster, 220 nanoseconds. So this already solves the problem for the 68HC11. But there's more, because you still see the command is clocked in 8 cycles, and that needs to be done for every single access. And that takes time. Now let's take a closer look at how the dummy cycles are arranged. These 6 dummy cycles, 2 of them are the so-called mode bit. If these mode bits are set according to the specifications of the vendor, it's different per vendor, then you can actually omit the next read command. So you shave off 8 cycles. And so you're putting these dummy cycles to good use, because you are announcing my next command is also a read, so you don't need to do that. So let's call this level 5B the bonus level. And this leads us to boss level, and that is hiding the command in the previous access. And that shaves off enough time so I can use very low frequencies and still get into the timing requirements of the 68HC11. Now, if we're looking at the Commodore 64, you might say, yeah, this is a 1 megahertz machine. 1 megahertz means 1,000 nanoseconds. We've got lots of time. Why do you even bother? No, we don't. The C64 is a 2 megahertz memory machine, so even if if the CPU runs at 1 megahertz, the memory runs at 2 megahertz because the video chip and the CPU are accessing interleaved. And then, of course, the address is not valid all the time. For a VIC access, it becomes valid really late, and for a CPU access, it becomes valid a little bit sooner. But on C128s, for example, the address comes a little later than on a C64. That's because of the MMU that's being used in the C128. And of course, everybody would expect that a cartridge that you sell for a C64 would also work in a C128, and therefore this needs to be taken as a worst case. Then, of course, there are differences between PAL and NTSC C64s. PAL is running at slightly less than 1 megahertz. NTSC is running at a little more. So NTSC C128, that's the worst case we need to design for. And given that the address becomes valid fairly late, and the data must be applied on the data bus about 60 nanoseconds or even less before the end of the access, otherwise the CPU won't catch it. That brings us to about 300 nanoseconds, so not very much different from those 270 nanoseconds that the 68HC11 requires. So now, if we want to implement this, the basic go-to thing used to be Xilinx CPLDs. The XC9500XL series has very nice properties for retro computers because it is fast 3.3 volt technology, but you can directly interface it with 5 volt systems because it's 5 volt tolerant. And yeah, then I requested those 40,000, a little more, because yeah, I'm buying 40,000 for my customer, 500 for me, and when I saw this offer, I was like, yeah, 1.02, that's just a little bit more expensive than my best price a few years ago. And then I looked again. This is 1,020 per 100, so $10 per chip. We're back to square one. AMD took over Xilinx, and I believe they just don't want to sell these anymore. They want to phase them out. I don't know. I mean, they must be smarter than I am. So the only way was to go old school and prototype this on a C64 purely with TTL chips. And this works and has a few advantages, which I'm listing here. The TTL graveyard, the bill of material is under $3. Of course, you have more assembly costs because not only do I use more chips, but every single chip needs a bypass capacitor, and of course a few resistors and everything. So assembly cost was a little higher, but compared to those $10 that was quoted by DigiKey, that's a savings of well over $200,000 for my customer. And since these SPI flashes can be ordered with a binary file pre-programmed, and that's dirt cheap, that's just a few cents per chip. That's even more labor savings, and their original 68HC11 design also contained a Xilinx CPLD, which I will eliminate from the design, and that's going to save them even more cost. And the solution that I've made here has a built-in cross-development solution, so they even have a possibility to debug their updated write-to-flash routine. And it actually secures availability of this product until the time that the business owner of my contractor wants to retire, and he says that's in 4 years. So now let's move to the C64. I also had requests from Protovision. Protovision is a publisher of games. You probably know them. Those who don't, check them out. They have cool games. And they requested for me to produce 1 megabyte cartridges. So they actually had a title that uses 1 megabyte. And they obviously used something very similar to GMod 2. GMod 2 is my cartridge that has 512K and 2K of EEPROM for saving high scores or game settings, whatnot. And Protovision has actually bumped up this design to 1 megabyte and wanted me to produce these. But again, same problem, couldn't source the components for any reasonable price. And at the same time, I exchanged emails with Chester Colchan. Chester is the author of Sam's Journey, in case you didn't know, so he's a very credible author. And during that email exchange, he asked me if I can do certain things like 16K banks instead of 8K banks for the C64, because that's making life a lot easier for him. And then, of course, GMod 2 was only a Hex 8000 cartridge, and those have an unfortunate property on the C64, and that is if you want to use interrupts, then these interrupts would always go through the kernel ROM. If you switch to your own vectors, so switch off the kernel ROM, then the original, then the cartridge also disappears. So there is no way on GMod 2 to have an interrupt vector pointing directly into your ROM code. So that has always been a drawback for him, and he was requesting a number of times that I can replace the vectors as well. Now this programming model that was, oh no, let's go back. I forgot one thing. If you look at this again, I have a publisher, and I'm talking to Chester Colchan. If you imagine that this would be one company, then I practically violated the chain of command. I got a request from Protovision, but I'm actually talking directly to Chester Colchan. In this case, they're independent parties. But for a contractor, for example, I usually tell them, okay, one of the conditions, if I want to work for you, one of the conditions is I want to be able to talk to anyone in the company. Really, literally anyone, even if it's the janitor, I want to be able to talk to those people because it's just way faster, more efficient, and I encourage every one of you to do the same in your company. If there is a chain of command or something, you always have to go through your manager who talks to the next manager and whatnot. That's very inefficient, very slow, very error-prone, and therefore I usually demand to talk to those people directly. And I encourage you to do the same. I mean, if you get fired for that, it's been the wrong company anyway. So, the C64 programming model that results from the discussions with Chester Colchan. If you have 16K banks, and if you have an 8-bit register for banks, that gives you a natural size of 4 megabytes, because that's 256 times 16K, that's 4 megabytes. These come in different banks. You can bank the 8000 and the 8000 bank separately, but you can also bank them at the same time. So a single write can switch a 16K bank, or you can choose to bank those 8K cartridges, 8K banks individually. There is a control register that allows you to switch those three. There's a third ROM area at the kernel, E000, and you even have a single page available in the I/O area for trampoline code, for example. This code for the E00 for the kernel bank will always come from a fixed bank. There is no banking, and that single page that's being shown in the I/O area, that also comes from a fixed location. No banking there as well. Those 8K banks can be switched individually, and now this goes into a little bit of coding. The DE area, like I said, I'm not a coder. That's just what I believe it can be used for. The fastest NMI exit, no. If, for example, you want to play back samples and you want to do that NMI timed, then you at some point need to exit from this NMI. The fastest routine would be writing the RTI instruction into the shift register of the CI chip. then jump to that. And when the CPU is reading that RTI instruction, the next cycle is a dummy read cycle, and that will access the interrupt control register and therefore acknowledge the NMI. That saves you a few cycles on acknowledging the NMI. Now, the possibility of since the CR that handles NMI interrupts is located at DD, so in the previous page, it might be possible to branch from this area directly into a CR mirror. Of course, a branch, if taken and if it crosses a page boundary, takes longer than a jump, but it might save you some more cycles. I mean, that's up to you programmers. Of course, it can just be used as general trampoline code, like it has been used, for example, on the retro replay or action replay, the original ones. So that's up to you. Now, developing for GMod 4 is intended to be very console-like. I want this to be cross-development. There, on the bottom of the PCB, there is a little field where a cable can be soldered to, and that will allow you to program the flash remotely and to reset the computer remotely. So you can write your code on a fast PC with an assembler, send the stuff over with a command line tool through a USB connected device. And of course, you can also use vice emulation. We're currently working on this. I'm not sure whether this is already in the latest builds, but that will happen. Now, that's for developers. Publishers also have a need for certain things, because if you want to flash a few hundred or even 1,000 cartridges, which is actually possible on certain C64 titles, that can't possibly happen on a Commodore 64, because 4 megabytes, that's equivalent to 24 floppy sides, and just reading these would take, I don't know, with the fastest fast loader, like 5 or 6 minutes, only reading, and that's not even taking into account that you need to bit bang talking to the SPI flash. So mass flashing a certain quantity of cards is something that should be done on a faster computer, on a more modern computer. So I'm going to offer a USB connected device with 2 expansion ports where you can flash one card and the other one can be exchanged at the same time. So one is always busy and the other will be exchanged. And my goal is to have a cycle time for full programming and verification of under 60 seconds. So publishers really can get some decent quantity and don't have huge labor cost of just programming these flashes. And then, of course, during development, you always get more ideas. And the next step for me would be a DMA cartridge. This is not fully verified yet. It's something that I discussed with a few people. Some say it's totally rubbish. Some others say this might be interesting. The idea of this cartridge is to have DMA only. So if the computer starts, the cartridge will write into C64 memory and then just lurk in the background and wait for the next command to do the next DMA. And this would make games possible that require loading or exchanging graphics, for example, really fast. I'm planning 3 modes. One is DMA from the flash into the C64 memory at top speed, but that of course means that the CPU is halted. And this is actually going to be a tiny bit faster than the C64 REU, because the REU is fairly inefficient at the because when it starts its DMA, it always wastes a full 3 cycles in order to wait for the CPU to possibly do its stack writes because interrupt service routines, for example, they cannot be interrupted with a DMA, and any busmaster needs to wait for the CPU to finish. And the REU and also the video chip, they do that in a fairly inefficient way. They just wait for 3 cycles, no matter if the CPU has already freed the bus or not. I have a logic implemented that checks if the bus is really free, and if it's free before those 3 cycles have ended, then I can already take over the bus. And that leads me to the second mode, which I call sneak DMA. And that would be really slow, but it would not interrupt the CPU at all. It would only look at those 3-cycle gaps whenever the video chip interrupts the CPU, for example, for a sprite fetch or for a bad line fetch. And if I'm detecting that the bus is free, but those 3 cycles haven't passed yet, I can sneak in a write access and, for example, play back music or do a slow copy, but, well, do something useful. And last not least, it was only a little bit of hardware to add in order to support memory-to-memory DMA transfer. And that would, for example, be for moving screen data in really high speeds. The bill of materials is about the same cost as GMod 4. It's fewer components, but it's more expensive components. So the overall cost is about the same. So this is my next step that I want to explore. So actually 2 cartridges in the works. And that brings me to the end. Thanks to the revision team for making this happen. Those funny road signs, they're actually from a real contest that the state of Georgia has held. I took some memes from Tina, Make Meme. Those waveforms are from the Wavedrum editor. Really nice thing if you need to make any timing diagrams in your job. Wavedrum, free tool, really good thing. Chester, I already mentioned him a number of times. His input was really valuable. Xaba Fekete, I'm not sure whether I'm pronouncing the name properly. He's also an author, and he actually requested a DMA-like cartridge. So that idea of GMod 5 was actually sparked by his email. And then, of course, input from my employees, Tobias and Peter, who both gave input on, well, positive and negative, because the DMA and stuff, that's a thing to discuss. Last not least, I did this presentation with LibreOffice, and yeah, that's it. We can turn to Q&A. Now you can roast me for creating a new platform or ask for, thank you. Because that's what I want to discuss with you. I mean, I assume that most of you are programmers, not too much hardware designers. And especially the DMA cartridge has caused controversial discussion within our company. And because it's kind of leaving the C64 compatibility realm. Of course, it does require the hardware. There would be no possibility to make a title that it can be offered as a download and as a cartridge. It would only work on emulation if we actually make emulation for GMod 5. Very likely that it's going to happen. But what I want to hear from you, if possible, if you have an opinion, is this creating a new platform, or would you expect GMod 5 as a viable 8-bit option because DMA has been presented for the C64 before, original Commodore, the REU? Let me hear.
Push comes to shove, it's the same hardware, the same expansion.
Not working though.
Not working?
Oh, it's working? Ish.
Yeah.
Push comes to shove, it's the same platform, same expansion bus, same everything. The fact that you're using it in an unexpected way, I think, is classic demo scene. It's not anything beyond that.
All right, thanks. There's one.
Could the GMod 5 be made as an REU compatible device, or could it have a mode that is REU compatible for games like Sonic uses the REU for DMA? Is that an option that you're thinking about?
I actually thought about it, but especially the Sonic thing is something that uses writes into the REU. So I believe the whole level data is kept in the REU, and whenever something on the playfield is changing, that change is stored in the RAM. So it actually requires RAM to be on the card, and RAM is not available at those low prices. And of course, talking to RAM is like SD RAM, which is pretty cheap, but that's more expensive logic-wise, and it's not as easy as these SPI flashes. So I actually talked to the author of Sonic, and like I said, writing into memory, that's required. And of course, I believe that setting up a DMA for the REU is pretty inefficient. You need to make a lot of write accesses, and then of course you have the freedom to use any order of register writes, but then you need to make another register write in order to actually initiate the transfer, and that all costs time. In my opinion, the C64 is all about saving cycles these days. And if you want to initiate a DMA, maybe even a recurring DMA, I want to introduce something like scheduled DMAs that you only initiate with a single write access, and you pre-scheduled the length and the source and the target. Or if you actually do length, source, target manually, I would define the order in which you do those write accesses, and whenever the last write access comes in, the DMA is actually initiated, so you don't waste another write cycle. So those are optimizations that I want to do in comparison to the REU. And I'm hoping that this saves some time for the programmers. More questions? It's Wally.
Will there be example code available upon release, so that we just can go from some routines and learn from this, except for studying the hardware manifesto and go in and trying to implement stuff there?
Yes, of course. I actually developed a similar cartridge already 2 years ago that was a lot smaller in capabilities, the GMod 3, which is actually fully described in our wiki, and it's even emulated in Vice, but it never came to fruition because I couldn't get those Xilinx chips. I thought that it was due to the chip crisis in 2020, and just decided, okay, let's wait a little until the chip crisis is over, prices come down, and then I can produce GMod 3, but that wasn't available. So, I mean, that didn't come to fruition. But back then, we have already published source code, example code on our server. Not sure whether, I believe it's a GitHub. No, it's not on GitHub, but it's a GitLab that we use to publish this code. It's all going to be linked from our wiki. So the whole programming model that I just outlined here in the seminar, that is also available already right now in our wiki. So you just go and search for GMod 4, and you have the whole programming model. And as soon as we have example code for that, it's going to be linked from there. So free access to the repository. So you don't have to reinvent the wheel if you want to do writes to the flash, for example. And actually, there's one aspect to GMod 4 that I haven't mentioned, and that is I am not using a separate EEPROM for saving high scores, but the actual flash chip can be used for saving high scores. And that enables you to not only save a few hundred bytes of high scores, but really to use hundreds and hundreds of kilobytes for large high-score lists or maybe comments that somebody wants to put in there. And you could do level editing because you have access to all the flash. And this programming would work from every machine, as opposed to GMod 2, where the writing to flash was only possible on certain versions of the C64. So writing was always kind of restricted, but it's not as restricted anymore on GMod 4. So if you are thinking of any game that would evolve where you want to do field updates, that's also an option with GMod 4. All right? Nothing else? Well, then let's wrap this up. Thanks for your time.